So welcome everyone, we'll get started. I hope your study's going really well. So we've got this exam we're going to work through today. This is from 2018 and it's what we call the SACE, it's the Asia Pacific Exam, because there are some people that live throughout the Asia Pacific that do SACE as a education certificate, and so this is the exam that the SACE board wrote for them. So I've got a copy of it and it's a good exam, it's indicative of all the stuff that they ask. It is a 3-hour exam, so I reckon we'll just do as much as we can in 2 hours. That'll be enough, and we should be able to get most of the way through it. And there may be some stuff that I'll sort of brush over, for instance the first page, that we won't spend too long dawdling on and so forth. So that's one option we have. Another, last year we went through one of the studies exams. In fact, it was, remember how it went from math studies to maths methods? So they changed the course in 2017, and so I pieced together a couple of studies exams to make an adapted one. But I've already made a video on that, so I can print that off for you if you want it. But there's just so many exams for you to go through. Nonetheless, we'll just follow the same style that we did last week, that we'll just sort of go through it together. Stop me anytime if you have any questions. I'll try to point out strategies as we're going. In 10 to 2 hours, let's get it done. Any questions? Cool. All right, so begin with booklet 1. That's what I recommend doing when you're doing the exam. And on the first page, all right, 69 marks in the first booklet, so I reckon we'll shred this. Okay, for each of the following differentiate. So, like I said, where we can, we will save time. On the first page, you must get all of these marks, okay? Everyone must know these skills. And so all I'm going to write down for the first page is just what rule you should use. So we got question 1A, that's a product rule, all right? So you've got your u is x squared and your v is e to the x, all right? You've got x squared times e to the x. If we look at b, that's going to be a chain rule because you have some function to the power of n. So you have to use the chain rule. And then for the last one, we've got a quotient rule. There's no way we can simplify that. For C, that's going to be a quotient rule. You've got u at the top, the ln function, and then you've got v at the bottom, which is just x. That's as long as I want to spend on the first page. All right, so they're skills that we need to have mastered, and we need to make sure we're getting all of those marks. Okay, let's move on. Question 2. Consider the table of values below. Okay, the function is continuous and increasing from -5 to -1, and the graph is shown below. An overestimate was calculated using 2 rectangles. G'day guys, so I'm out of booklets, but if you're happy to just look it up and write it down, you got your pad? Yep, excellent. So this is called the SACE Asia Pacific Exam. So it is booklet 1, booklet 2. You'll be able to find it on the OneNote or have a look at Tammy, happy to share with Lanny a bit, maybe, and so forth. Okay, an overestimate was calculated using 2 rectangles. The result is, and we've got it here, 2.8. So you can see the width of each rectangle is 2, and then they've used the heights there. On the graph above, draw the rectangles used to calculate this overestimate. So I'll provide a rough sketch of the graph, and we're doing an overestimate from -5 to -1. So if we're doing an overestimate, that means they're the upper rectangles, aren't they? So we're starting here at -3, all right, which has a height of 0.5. So you can see we have the width of 2 and the height of 0.5. And then the second rectangle, we're going to start at this point here, which is, that's the x value, by the way, -1, and then going down. So they're the 2 rectangles that it wants you to draw. You get a mark for that. Okay. Now it wants you to calculate the underestimate for the definite integral using 2 rectangles of equal width. So for the underestimate, this time we're going to start here, aren't we? So we're going across and down. So you can draw them either on the graph you've got here. You don't have to even draw them, you just need to calculate it. So we're going across and down, and then from here across and down as well. That's going to be our underestimate. And so the underestimate is going to be the width, which is 2, multiplied by the height. So the height of the first lower rectangle will be 0.1, and the height of the second lower rectangle will be 0.5. So we'll evaluate that. 0.2 plus 1, 1.2. Is that all of you found it, have you? Or you? Yep. Sam, you're okay? Yep. Okay, so that's that. 2 marks there, and then calculate an improved underestimate for the definite interval using 4 rectangles. All right, so these are very generous marks, right? Okay, now we're going to get four intervals. So we're going from -1, -2, -3, -4, -5, and we're using 4 rectangles, so that means we're just going to halve these rectangles. So we're still doing an underestimate, so there's the first one, there's the second one, that's the third one, and then this will be the fourth one. Okay? So for part C, the width of each rectangle is 1, so we don't really need to consider it as a product. It's not changing the value of it, it's 1 times, and then we're just adding the respective heights. So we'll have 0.1, 0.2, 0.5, and 0.8. 0.1 plus 0.2 plus 0.5 plus 0.8. And so 1 times each of those, right? So we've got 0.3, 0.8, 1.6. Okay. Done. Okay, so everyone's hopefully all right with that, understanding how we're getting those numbers and so forth. Again, if you feel like there's an issue, make a mark of it so you can ask me or interrupt me. Please ask a question if you need. Otherwise, I'm going to assume you know what I'm talking about. Good day, Christina. So, maybe follow along with Lydia and have a look at the bring up your laptop. I've got it. Well, I'm going to bring it up here too. So guys, maybe just on that, I did send out a forms request so I knew how many exams to print. So some people here didn't answer the survey. So if you didn't answer the survey, you know, maybe you shouldn't have a copy of the exam. Thank you for those that did. I printed more than was needed, so a couple of people didn't answer the survey. All right, let's continue. So we've got consider the discrete random variables x. All right, so we've got possible events, x1, x2, x3, x4. And then we have the probabilities of those events as well. So I'll bring it up here so you can have a look. And hopefully I'll remember to scroll along. So we've got what condition must each probability satisfy? So each probability satisfy, and then if you look at part 2, it's asking what condition must all of them collectively satisfy? So it's making a distinction about the 2 properties that a probability distribution has to follow. The first that each has to follow is that each probability is 0 or positive. So each value of P must be greater than or equal to 0. All right, so you can't have a negative probability. So that's our answer to A part 1. And then for A part 2, we have what condition must they satisfy collectively? The sum of all values of P is 1. All right, now we have a probability distribution with some value of K. Part 2. Show that the sum of 2k squared plus 3k take 2 equals 0. All right, so a couple of ways that can be done. The first would be to suppose the sum of all values of k has to be 1, right? So let's go through with that. Because the sum of all probabilities has to be 1, then the sum of each of these has to add up to 1. So we're going to have, so this is B part 1, we'll have, if we take this property, the sum of P is 1, therefore k on 4 plus k squared plus k on 4 equals 1. All right, so all I've taken is the probabilities of each respective event. and made them sum to 1. And then we'll start to collect like terms, right? What do we have? We're going to have k squared plus, we've got k on 4 plus k on 4. That's 2 lots of k on 4, which is half of k on 2, plus k. They're like terms, so we're going to need to add them, sorry. K on 2 plus k, that's going to be 3k on 2. All right, it's 1 plus a half, that's 1 1/2, 3 on 2. And then take 1. And then multiply both sides by 2. That's going to give us 2k squared plus 3k, take 2 is 0, as required. Alright, so all we're saying is the sum of all probabilities is 1, and then we're just collecting like terms and making it the same expression that they've got. Find the value of k for this distribution. Alright, so from here we've got a quadratic that we need to solve, right? This is what we're trying to solve, and all they want you to do is find it. So you can just go straight to your calculator, and you can factorise it as well. If maybe it's a good point to talk about where we can factorise quadratics in our calculator. So we'll just go menu, equation solver, and we'll go to polynomial. Okay, a quadratic is a type of polynomial. Any function of the form x to the n is going to be a polynomial, right? And the degree is 2. The degree is 2 for a quadratic, and then you're just inputting the coefficients of k. So we've got 2, 3, and minus 2. Now this one should be reasonably easy to factorise. All right. So you just type in those coefficients, press execute, and we've got k equals 0.5 or k equals minus 2. And we have to reject one of these solutions. Which one do we need to reject? Negative 2, because we can't have negative probability. Very good. Okay, so now they want us to complete the table using the value of k that we found. So if we're doing that, we've got the events, which are 1, 2, 3, 4. And then the probabilities. So in the first cell, we've got 0.5 divided by 4. All right, 0.125. So just putting all of those, you can put them in the calculator. 0.5 divided by 4. 0.125. All right, and event 4 has the same probability as well, 0.125. And then we have 0.5 squared, which is going to be 0.25, and k is 0.5. Alright, so just filling that in, get to your mark. Okay, find the exact value of the mean. Alright, so the mean of a probability distribution is each event multiplied by the probability of that event. Alright, so we'll have the mean is 1 times 0.125. 2 times 0.25 plus 3 times 0.5 plus 4 times 0.125. Oh, g'day Gabby, another one. I might print some, guys. Alright. So I'll press print, someone's gonna have to go grab them. I'll just print 4 copies. And don't click 1, 2. So maybe just wait a few minutes, and then Sam, do you want to go grab them in a couple of minutes? Yeah. Alright, so where will we up to? Question 3. Alright, anyone evaluated that for me? So what have we got? 0.125 plus 0.5 plus 1.5 plus 4 times 0.125 is 0.5. So there we go. 2.5, 2.725. Everyone happy with that? Anyone done a better job than me there? Okay.
Is it 7 or 6?
6, sorry, 5.1. All right, next we've got to calculate the standard deviation exactly. Now you need the mean to calculate the standard deviation, and there's a couple of ways to calculate the standard deviation. The formula is on the formula sheet that SACE provides you. I can't remember it, so let's have a quick look. So it's in exercise 7D. We've got two formulas. Let's go for this one here. Square root of the sum of each event squared multiplied by the probability, and then take the mean square rooted. Okay. So the sum of each event squared multiplied by the probability. So we'll do that first, then we'll take away the mean. So let's write it out as a big long-winded expression first. So the sum of the square root of each event. Okay, the first event is 1 squared, multiplied by the probability of the event 1. So multiplied by 0.125. Okay, plus, all right, the sum of the event 2 multiplied by 0.125 plus, and then plus,
Number 2, there's no 1 in it. Is there?
no, you're correct. And then 4 times 0.125. Alright, let's lose some space so we keep going horizontally. Okay, so each event's squared multiplied by its probability, all added together. So that's the first component, right? Take the mean squared, and then square root. Okay, and there are some parts of that can be simplified. Find the exact value. Yeah, so I mean we can simplify some of these components of it and add those parts together, but we won't be able to simplify it too much. All right, so I'll leave that with you. Let's move on. Question 4. Okay, consider the functions f of x and g of x, where f of x is the root 3 cos of x on 2, take x squared plus pi squared, and g of x is minus x squared plus pi squared. These two functions form the boundaries of the shape as shown on the graph below. The intersections marked at A and B lie on the x-axis. Find the exact coordinates of points A and B. Okay, so 3 marks here to determine where they intersect. Now, there's 2 ways you can do this. Okay, because you're told that these points lie on the x-axis. So one way to do it is to make the functions equal to one another, right? Root 3 cos of x on 2, take x squared plus pi squared. So when f of x equals g of x, okay, so we can do that. But you also know that it occurs when they lie on the x-axis, which means you can make the first function equal to 0 or the second function equal to 0, because that's when the roots are going to occur. And it's much easier to make the second function equal to 0. There's just less problem solving involved. Either of them is going to generate the solution, but the solutions here are going to be the same as the solutions here, which are going to be the same as the solutions of this one equals 0, because the solutions occur on the x-axis. We're told that. All right, so it's just a faster way of doing it. If we solve this, we have x squared is pi squared, we have x is the square root of pi, plus or minus. All right, so look at that, 3 marks just for writing that. So you've got A, okay, maybe here's where the trick comes in. Find the exact coordinates. So they're not just looking for x values, this is where it pays to read it carefully, they're looking for y values as well. So for A is going to be minus the square root of pi. And the y value is obviously 0, right?
Is it not just pi by itself?
Sorry, you're correct. The square root of pi squared is pi. Gee, I'm not doing too well today. Been on holidays. Yeah, good, cool. All right. So we've got the x value, and probably where you're getting the third mark is stating that y value. And that would have tripped a number of people up. They look at it, they go, I've got the x values done, move on to the next part. All right, so it pays to read it carefully. All right, they should be done now, Sam, those booklets, if you want to go grab them. Yeah, down at the copier, and yeah, one for you, Christina, Gabby, and Julio if you want a copy. All right, hence or otherwise, write an integral expression for the area of the shaded shape. So the area of the shaded region is going to be from minus pi to pi. The top function, take the bottom function. Okay, what's the top function? F of x, which is the root 3 cos of x on 2. Take x squared plus pi squared. Okay, that's the top function. Take away the bottom function with regards to x. Okay, we get 1 mark for making that statement. Okay, and then part C wants us to go ahead and solve that integral. Find the exact area of the shape. All right, so I'm just going to continue down from here. I've got minus x squared, take minus x squared. So that's minus x squared plus x squared. They're going to cancel. All right, so like we can see those cancelling. We've got pi squared, take pi squared. That's going to cancel as well. So this is the integral that we're solving, right? Root 3 cos of x on 2. Now remember I've said, whenever we have cos of x on 2, it's the same as half of x. Okay? I cannot emphasize that enough. Anytime you see x on top of a number, you bring that number out front, and now it's just a times x, a times x. All right, so that's the integral that we're solving. Even then, the root 3 can come out the front. Okay, it's just a number that's hanging out, so that's what we're performing the integral of. So let's bring the root 3 out the front. The integral of cos of ax is 1 on a sine of ax. So this is going to be 1 on half sine of half x, and 1 on top of half is 2. Okay, just continuing on, just plugging the pi in there then. We have 2 sine of, we've got half times pi, so that's half pi, or pi on 2. And then we'll have to take away 2 sine of half of negative pi, square bracket. And at this stage you can start to put that stuff in your calculator. 2 sine of half pi, that's going to simplify to, now sine of half pi is the same as sine of pi on 2. If you think of your unit circle, okay, I'm just drawing connections here. Sine is the y value, pi on 2, so the top of y value is 1. This simplifies to 1. So we have 2 times 1. This whole thing here simplifies to 2. Take away, this is going to be negative pi on 2. So it's 2 take away negative 2. And then we have this root 3 out the front. Root 3, 2 take away negative 2 is 4, so we have 4 root 3 as that area. Okay, that's what it simplifies to exactly. All right, very good. On to question 5. So everyone got a copy then? Yep. Okay, we have, consider the function ln of 3x plus 8. For what values of f of x, is f of x undefined? Okay, so read it carefully. ln of x, right, is defined for x is greater than 0. That's the value greater than 0. So that's the values for which ln of x is defined. So that means it would be undefined for x is less than or equal to 0. So this function here is going to be undefined for 3x plus 8 is less than or equal to 0. And then we just solve that inequality. Remember, an inequality is the same as an equal sign unless you multiply or divide by a negative, in which case the inequality switches direction. So this is 3x is less than minus 8, and we divide both sides by positive 3. And so because we're dividing by a positive number, the inequality stays in the same direction. All right, if you're unsure of those, let me know, and I'll point out where we can practice that skill. But yeah, that's definitely part of our course. Using algebra, solve the equation f of x equals 0. Okay, so that was part A. You looked at part B. We've got ln of 3x plus 8 equals 0. Okay, to solve a logarithmic equation, we need to raise e to the power of both sides, right? So we'll have e to the power of ln of 3x plus 8 equals e to the power of 0. Now, e to the power of ln of 3x plus 8 simplifies to 3x plus 8, and over here, e to the power of 0 is 1. And now we're solving that with the equation. 3x equals 1 take 8 minus 7, x is minus 7. That's part B. And then part C, evaluate f of 0. So this is where we put x is 0 into the equation. That's going to be 0, it would be ln of 8. Okay, on the axis below, sketch the graph, clearly showing and labeling the information that you've found. Okay, so because we've found, right, it's undefined for values less than minus 8 on 3, that's the same as minus 2.666. That's where our asymptote is occurring. Okay, so we've got a vertical asymptote at minus 2.66. They've even given us the thirds. How good is that? So let's sketch it. So here's minus 1, here's minus 2, here's minus 3, here's the asymptote. Okay, vertical asymptote there. Then we have the x-intercept at minus 2.3 recurrent, or minus 230. So what did I have? I have minus 1, minus 2. So here's the x-intercept. And ln 8, let's evaluate that to a couple of significant figures, just so we can identify where it crosses the y-axis. 2.07. So here's 1, here's 2, it's just above 2. And so it's going like this. And you can get all of that information from your graph. You can open up your graph, all right, and you can g-solve this, and you can g-solve that, and you can anticipate, yep, this is the shape that it's going to take. So you don't need to have answered all these parts to get the 3 marks here. Now, remember, when they're giving marks out for a graph, they're looking for all of the key properties, right? So you're getting 1 mark for the asymptote, and 1 mark here, and 1 mark here. All right, and they'll draw a box. All right, so you can't just say, oh, it's approximately here, it's above 2. It has to be exactly, you know, in that right region. You know, they do have a little bit of leeway, but you can't just sort of go, it's roughly there. Be specific about what region it lies in. It should be as close as possible. Okay, so then moving on, they repeat basically the same question here, but with a logarithmic equation in general form. So the thing here is that not much is changing. Okay, we have the equation of ln of bx plus c, and they say find the equation of the asymptote. All right. Well, the asymptote occurs when this part's equal to 0. Right? When bx plus c equals 0, we can see that's where the asymptote occurs because it's undefined for values after that. So we'll have bx plus c equals 0, bx is minus c, x is minus c on 2. The same operations apply with letters as they do with numbers. And what you'll notice here is relationships between this statement and this one, and the next statement that we're going to make. Okay, the next statement says find the coordinates of the x-intercept. Okay, so the x-intercept occurs when y is 0. So that means ln of bx plus c equals 0. Put e to the power of both sides. We'll have bx plus c is 1. so that was part F. So we've got part E, part F, and then part G. Find the slope of the tangent when x is 0. So if this is the function, we need the derivative function, so we need g dash of x. So when you differentiate bx plus c, you're going to get b on top of bx plus c. That's the derivative function. We want to know the derivative when x is 0, the slope when x is 0. Alright, so I've assumed a few things there, like I've jumped straight from a logarithmic function to its derivative, okay, and then I've just chucked the x value in. So hopefully we're feeling alright about that, and we are moving along nicely. Oof, imagine locking up at 9:30. Okay, question 6. Let x be a continuous random variable with probability density function f of x. Which of the following statements is true? So we have a probability density function. Okay, so let's explain what each of those means. So the first one says f of x is greater than or equal to 0. What this means is the y value, all right, remember y equals f of x. So f of x, whenever you see that, that's talking about the y value. The y value must be greater than or equal to 0. Okay? The second one, 0 is less than f of x is less than 1. It's saying the y value occurs between 0 and 1. Alright? Might be the case, doesn't have to be. And the next one says f of x can take any real value. That means f of x can be any real number. Can be minus 1,000, can be minus 1,109.746. Alright, that's what it means when it says take any real value from any real number. Okay, so the box we should tick is the first one. Alright? Because it's a probability density function, all probabilities must be 0 or positive. Okay? The second one. Because you can't have a probability larger than 1. Okay? So, yeah, a little trick there. So they're correct that the probabilities must be positive, but they can't be larger than 1, can they? So 0 is less than f of x is less than 1. Alright, so that's maybe, if we just click back then, because maybe we weren't precise enough with question 2. Question 3. If we flick back there, what condition must each of P1, P2, P3, P4 satisfy? I said they must be greater than or equal to 0, but they have to be between 0 and 1, can't they? Alright, so let's fix that up. 0 is less than P is less than 1. So that's question 3, part A, part 1. Okay? So, yeah, that's good. We shouldn't just write they have to be positive. They do have to be positive, but they can't be larger than 1. Alright? Alright, that's good. So that's sort of ticking over in our mind. Okay, which of the following statements is true? Tick the appropriate box. So we have the sum from minus infinity to infinity of the function is 0. The sum from minus infinity to infinity of the function is 1. The sum from minus infinity to infinity of the function could be any real value. Okay, so we're not given constraints on the probability density function here. So the correct answer is going to be the last box. Okay, it could be any number. All right, it's only when we're given constraints for the validity of the probability distribution density function. So the last box, give that one a tick. All right, on to B. The graph shows a straight line that represents the probability density function defined for between 0 and 4. Okay, so you can see if you were to do the integral of this function from minus infinity to infinity, it's going to be some value, right? It's going to be some value. It'd be 0 because each side will eliminate. Nonetheless, let's move on. Part 1. Show that the function is 1 on 8x. Okay, so what do we have here? We have the equation of a straight line going through 0, 0, and the point up here is 4 and f of 4. Why haven't they given us a y value? X value and y value. Are we told anything else on the previous page? We'll just make check if it printed did some logic to it thing. I reckon there's something happening there. I might need to fix up. So let's talk about how it would be done if we had the coordinates stated correctly. So for the equation of a line, is y equals mx plus c, right? The y-intercept is 0, so that means the c value is 0. So we have the equation of the line y equals mx. We need the slope, n. The slope is y2 take y1 on x2 take x1. And in our circumstance, okay, we have f of 4 take 0 divided by x2, 4 take 0. And so we're left with f of 4 divided by 4. And so because we're not given that y value, it's going to be tricky to get it to the 1/8 of x. Can anyone see a solution there? Yeah, I reckon they haven't listed that coordinate properly. F of 4. Anyone see? No, alright. Cool, so let's assume they're on their part. Okay, write an integral expression for the mean of the probability density function. So this is in chapter 9 that we did this. So the mean of a probability density function is the integral from a to b of x times f of x. So in our circumstance, that's going to be the integral from 0 to 4 of x times x on a with regards to x. You get 1 mark just for writing that. Part 2, evaluate your expression. Alright, so in part 2, so that's part 2, in part 3, evaluate your expression. Here, you can just use your calculator. You can go through and integrate it if you want to. I mean, they'll probably both take roughly the same amount of time. So, calc integral, we've got x squared on 8 from 0 to 4. And we'll have 8 on 3. Okay, find the probability of the density function being larger than the mean. Alright, so if this is the function, right, and we saw the mean was 8 on 3, which is 2.6, okay, that's here, and they want to know the probability of this event, well, it's going to just be, so for part 4, its probability is the area under a curve from 8 on 3 to 4 of the function x on 8 with regards to x. So just type that one in again. So we've got 8 on 3 to 4, 5 on 9. All right, very good. All right, any questions? So, the sign diagrams below relate to the first derivative f dash of x and the second derivative f dash dash of x of the function f of x. Alright, so that's it there. For what values of x is f of x decreasing? So, f dash of x tells you the slope. A function is decreasing when the slope is negative. So we're just going to look at the sign diagram for f dash of x, and we can see it's negative between -3 and -1, and -1 to to positive 2. Alright, everyone see that from the first sign diagram? The slope is negative in the those regions. Alright, for what values of x is the graph concave? Okay, so concave and opening downwards has the sign diagram of the second derivative is negative. So we'll have, so that's for part A, is part B. We'll have x is less than -2 and -1 is less than x is less than 1. Alright, so it's opening downwards between those two values. The function has three stationary points, A, B, and C. Determine the coordinates of A, B, and C and classify each as a local maximum, a local minimum, or a stationary inflection point. Write your answers in the table below. Okay, so we've got A, B, and C. And we've got the x coordinates. Okay, so the first thing we can see is stationary points occur when the first derivative is equal to 0. That's the roots of the first derivative, right? That's when the slope is 0. It's not increasing, it's not decreasing, it's stationary, it's horizontal. So the first one is that x is -3. And what we can see there is we had positive slope, we were increasing, and then we started decreasing. So if we have positive slope to negative slope, we have a local max at -3. Okay, then what we can see is it's decreasing. It goes horizontal at -1, that's where it's equal to 0. It's decreasing, it goes horizontal, but then it keeps decreasing. So it looks like this, right? We had our local, we'll draw it in a sec. We had our local max, it's decreasing, it goes horizontal, and then it keeps decreasing. What do we call that? Stationary point of inflection. Concave up, concave down. It's changed shape at that stationary point. So this is a stationary POI. And then the last one, C, we can see x is 2, all right, is where the slope is 0 again, and we're decreasing, then increasing local mean. All right. On the axes, labeling the points A, B, and C as per the table, graph the function that passes through the point -1 f of 1. Okay, so -1, I'm just going to go straight off what I've done here. Let's talk about what we've seen so far. We have a local max at x is -3. All right, so I'm going to put the x-axis here. All right, and the y-axis here. We've got x is -3, -2, -1. All right, so we have a local max at x is -3. We have a stationary point of inflection at x is -1. All right, and then we have a local minimum at x is +2. So that's over there again, but there's a local minimum there. Okay, we don't know how far down it goes. You know, we don't know where the y-intercept is. We don't know that kind of stuff. We don't know where this root is or anything like that. Doesn't matter. Okay, what we're interested in is getting these points in the right spot. Okay, so that's what on the graph, sketch f of x. We've got the stationary points A, B, and C. I think they would accept it. Remember, the marker is looking to give you marks. Yeah. If you're unsure, though, I would probably write the whole thing to be safe. They would probably reward the marks. So yeah. Okay. All right. Question 8. We've got calculate the integral from -1 to 1. Write your answer in the appropriate space in the table in part C. So just on your calculator, I would just bring up the integral from -1 to 1 of x to the 3, take 3x plus 2. And let's generate the table so that we can start to notice a pattern here. So we've got k, 1, 2, 3, 4, 5. We've got some values filled in. 12, 16. I can already see the conjecture, I reckon. 84 maybe? Anyone done it? Just to make sure. So integrating from -1 to 1. Get 8, 12, 16. Calculate for 2, so we'll get 8. Calculate it for 5, and we'll get 20. Okay, so then we're making a link between this value of k and the area. Alright, so if k is 1, we saw the value of the integral. I shouldn't say area, because it's the value of the integral. If k is 1, the value of the integral is 4. If k is 2, the value of the integral is 8. So what's the relationship between the value of this integral and k? It's equal to 4 times the value of k. 4 times 1 is 4, 4 times 2 is 8, 4 times 3. And then prove your conjecture. So these integral ones are nice conjectures to prove, because all you have to do is solve this conjecture. You're just going to evaluate that, and it should come out the wash as 4k. So we'll integrate this. We'll have x to the 4 on 4. Take 3x squared on 2 plus 4x.
Pretty sure it's +2.
What am I missing? I wrote it out wrong. +2. Thank you. That did say 2 as well. Yeah. Plus 2x. From minus k to k. Alright, so then we'll perform the substitutions. We'll have k to the 4 on 4, take 3k squared on 2 plus 2k, take away. Alright, watch this. Minus k to the 4. I'll out your way on 4. Take 3 to minus k squared on 2 plus. Okay, so what's going to happen here, when you have minus k to the 4, that becomes positive k to the 4, right? Because when you have a negative number to an even power, the negative is going to cancel. Alright? And so what that means, we've got k to the 4 on 4, and here we've got k to the 4 on 4, and we're subtracting it, those parts are going to cancel. The same with this one, it's to an even power, and here an even power, so those parts, take 3k squared, minus 3k squared. So we're subtracting it away, that's going to cancel. And then we've got 2k take away negative 2k, 4k. 4k Ultra HD. There's the solution. Alright, shred it down. 69 marks in 48 minutes. Booklet 1 does tend to be easier. Okay. We've got Try is a student at a school that has a total of 1,000 students. Try has some news that no other student knows. One day Try enters the school at 8 AM and begins telling some students this news, which spreads among the students in the school. The number of students in the school who have heard Try's news at time T hours after 8 AM can be modeled by this function. According to the model, how many hours will half of the students in the school have heard Try's news? So, this is the model. 1 plus 999 is like 1.386 T. And we're asked how long. So we're asked to find a time value until half of the students know it. And there's 1,000 students, so half of them is 500. So, a couple of ways we could do this. You could type that into equation solver. We can graph this function. I think it's going to be useful to graph it. I'm just anticipating, look, there's an empty graph space there. Okay. Graph it, G solve the x values when y is 500. So I'll do that for us on Desmos so we can all see that the function graph it accordingly. So our function is 1000 on 1 plus 999 to the minus 1.386 x, I should do. And remember, you know, even if you're anticipating, they've given you a v window there, so I'm just going to go, yeah, we've got a graph of 0 to 10 for x, and for y, we've got 0 to 1200. That's what it looks like. We want the y value when x is 500. Y is 500. We want the x value. 4.983 hours. So the solution in part A, 4.983 hours. Alright. On the axis below, sketch the graph clearly showing any intercepts and asymptotes. Okay, so as far as intercepts go, we're going to have a y-intercept of 1, all right, which is a bit difficult to illustrate on the graph. Because they've said clearly illustrate it, that means we're going to have to label that point, I reckon, just to make sure we get the marks there. So this is clearly illustrate that that's an intercept. So we're going to write that as a coordinate, 0, 1. When x is 0, the y value is 1. And it's a limiting function, all right? So if they've said any asymptotes, well, have a look at what's going on here. Okay, we can see that horizontal asymptote at y is 1000. So we sketch the y is 1000, and then this is the sort of shape it has. And this is probably a good example of where you need to get, in order to get the 3 marks, we should have the shape correct. So it seems to be that point when x is 4.983, so here's 5, here's 10. When x is 4.983, that's when we have the 500. Alright, so there'll be a box there. That's where they want you to hit that point. Alright, and what's happening there, roughly what we can see, is that seems to be where the point of inflection is, where it changes from concave up to concave down. So we have to illustrate that shape. Concave up, concave down. Okay? So that would be the shape that we're looking for, and that coordinate that passes through. Okay. C part 1. Find an expression for the rate at which TRI's news is spreading among the students in the school. Okay, so if this is the number of students that know it, then the rate at which it's spreading is going to be n dash of t. Right, so we need to differentiate this function here. So n dash of t, and in order to differentiate that, you can use the quotient rule if you want to, right? We've got this 1000 at the top, but you don't need to, because I'm not going to differentiate it straight away, so I'll just call this n of t. I think the best way to think about this function is it's 1000 multiplied by 1 plus 999 e to the minus 1.386 t, and that's to the power of minus 1. Okay, we can bring it to the top and make it to the power of minus 1. And now this is just a number, and now this, to differentiate that, that's just going to be the chain rule. Okay, we have a function to the power of n. Okay, so to differentiate then, the 1000 is going to hang out the front. and then we have n, f of x, n take 1. Alright, so n is minus 1. n, f of x, to the power of n take 1. Alright, and then multiplied by f dash of x. So multiplied by the derivative of what's inside here. So when we differentiate the inside, the derivative of 1 is 0, so that part's gone. And then we're differentiating this component. I'll do it in maybe a couple of, well, one step, we'll just make it look plain. 999 multiplied by derivative of e to the 1.386 is minus 1.386 e to the minus 1.386 t. Alright, that number's just hanging out the front. E to the kx goes to k e to the kx. Alright, so that's the derivative. Now that 5 there is not a power, that's part of the graph. Okay, and we can simplify that, and in fact we're going to need to for the second part. So I'm going to treat C part 1, I'm going to simplify it first and then I'll point out where we get to C part 2. Alright, so what does this become? Firstly, that's going to be minus 1,000. And then we have this 1 plus 990 e to the minus 1 to the minus 2. I'm going to put that at the bottom. Alright, and make the power positive. So far I've done that component of it, and then we're interested in this component of it. Let's evaluate that. To simplify a little bit. $13.84, $13.85 and round it. Okay. So let's leave it like that. In the next, so that's C part 1. In the next step though, we will change it a little bit more. Hence, show that n dash of t is greater than 0. The rate of change is always positive for t is greater than 0. All right, so what we're going to do here then is we're going to take each component and we're going to demonstrate that this component's positive, okay? And because this component's positive, therefore, that component's positive and this component's positive, therefore the product of them will also be positive. Hence show that n dash of t is greater than 0. So if we let's take this part of it first. All right, we have minus 1,000. That's going to be negative. Minus 1,000 divided by, and this number is going to be positive. Oh, here, that's negative, right? So this whole thing is negative, and we have a negative times a negative, so this is positive. So yeah, that negative and that negative, but they cancel one another. All right, so that's all good. Okay, so let's show that this part's positive. Well, 1,000 is positive, right? So let's take this component then. We have 1 plus 999 e to the minus 1.386 t. All right, now that's squared. All right, now this must be positive because it's squared. Doesn't matter how negative it is, whatever you square it, it's going to make it a positive value. So we can say this component, like we can make the argument pretty clumsily and it will still work. must be positive as in squared. Okay, so if this component is positive, as in the denominator, therefore this must be positive, because we have a positive divided by a positive. Alright, so that part's positive. And then let's focus on the next part, the 1385. And we have e to the minus 1.386t. Now one way to think about that is that's e to the positive 1.386t at the bottom, right? And so e to the 1.386t is positive. All right, it's an exponential function. We're considering positive values of time. Excuse me. Therefore, and I won't write the whole thing out again, but we'll just write therefore n dash of t greater than or equal to 0. Okay. So they can be a little bit tricky, right? But the point I think of it is to isolate each component and talk about each component's positive, therefore the product of them is going to be positive. Okay, comment on the reasonableness of using this model. Now what they're looking for here is, we found the rate at which the rumour is spreading, and we've found the rate at which the rumour is spreading is always positive. All right, so that means, what that would mean is more and more people are always learning this rumour, okay? But that can't be the case because there's only 1,000 students in the school. So that's what they're looking for. So comment on the reasonableness of using this model. So we need to talk about the rate of change. It assumes the rate of change is always positive, which it can't be because there's a finite amount of people that can know the rumour. Reasonable as t gets large or t approaches infinity, because always positive. Okay, in one particular city, there have been many thefts of student possessions from schools. In an attempt to reduce these thefts, the government has provided new lockable cupboards to all schools in the city. Each student at each school has been assigned a separate cupboard and has been instructed to store their possessions in their cupboard and always keep it locked. The government conducts a survey of school students to determine how many always keep their cupboard locked. From a sample of 320 junior secondary students, the following 95% confidence interval for the proportion of junior secondary students who always keep their cupboard locked is calculated. Part A, explain the meaning of this confidence interval. Okay, so we're going to explain, what does the confidence interval mean? What does it represent? So for part A here, based on the confidence interval, we are 95%, yeah, confident that the true proportion of junior secondary students who keep their cupboard locked is between, I don't think you can list the numbers. Okay, that's what we mean when we have a confidence interval, right? It's a statement about how confident we are of the true proportion or the true mean lying in between that interval. Okay, part 2. What proportion of students in the sample always keep their cupboard locked? So we saw the confidence interval is between 0.797 and 0.878. Now the proportion from the confidence interval is always going to be halfway between them. We're not given the value of p hat, that's the observed proportion, but we need to calculate it. It's always halfway between them, so it's going to be the average. So what's that? Alright, p hat, the sample proportion is 0.8375. Hence, how many of the 320 students in this sample always keep their cupboard locked? Well, remember, x divided by n gives you the p hat value, right? That's how we calculate p hat. We're going backwards here. We're saying how many keep them locked out of 320 gives us that 0.8375. Okay, so to get x, we're going 0.8375 times 320. (268 students). Okay, and what you'll find then is if you do 268 divided by 320, okay, if you go, we did the survey, this many students have their locker locked, out of this many, that's where they've got the p hat value from. We're just working backwards in this circumstance. Okay, part C, it is suggested that senior students are less likely than junior students to always keep their cupboard locked. Therefore, the government surveys a sample of 120 and finds that 74 of these students always keep their cupboard locked. Calculate the 95% confidence interval. So we're just going to do this straight in our statistics mode. So stat, test, z, and it's a proportion. Sorry, not test, we've got 95% confidence, and we saw 74 successes out of 120 students, 0.5296. 5296 and 2.7036. Okay, so to 3 pigs, 526. And just a reminder, in the middle here, that's not p hat, that should be p, because p hat we use to calculate the confidence interval, which tells us the region for which the true value of p lies. Okay, can the government conclude that senior students are less likely than junior students to always keep their cupboard locked? Explain your answer. So, for junior students, the lower end was 0.797, right? 0.797, and for senior students, the highest it could possibly be is 0.704. So the answer is, let's read the question. Can the government conclude that senior secondary students are less likely than junior to keep their cupboard locked? Yes, as the confidence interval for senior students is completely below. So I think that might be a a typo there for 3 marks. Maybe it's 2. Alright, on to 11. Concerns have been raised over the number of times per day that teenagers check their mobile device. A study investigated the number of times that per day that teenagers check their mobile device. A random sample of 100 teenagers was taken, and the number of checks per day, X, was recorded. The sample mean was found to be X bar, 62.33. The sample standard deviation was 19.31, which is assumed to represent a good estimate for the population standard deviation. The histogram below shows the number of checks per day for this sample of 100 teenagers. Okay, with reference to the histogram above, explain why it's not appropriate to use this sample to calculate a confidence interval for the population mean. Okay, so confidence interval assumes a normal distribution. We can see above the distribution is not normal. Okay, so we just say as X is not normal, it is not appropriate to, we can just say as X is not normal. So part A, 11, because, yep, X is the distribution, so not normal or not bell-shaped or does not follow a normal and not a symmetrical distribution, either of those would be fine. Okay, over the next page. Suppose that many random samples of 100 teenagers were taken, and the sample mean X for each of those samples was recorded. The histogram below shows the sample means. The central limit theorem applies when the size is sufficiently large. With reference to the histogram above, explain why in this case the sample size of 100 is sufficiently large. It's approximately normal. So this is part B. Because the histogram, the distribution is approximately normal. Alright, flip that over. Using the sample of 100 teenagers considered in part A, calculate the 90% confidence interval. So following the same thing here, except we're doing the first sample. And so interval test is in the first sample. Is in the first sample. 90%. So we have to set our confidence level as 90. 90, standard deviation was 19.31, and they said we can use the sample deviation to approximate the population, and the mean was 62.33. Okay, using a sample of 100 teenagers considered in part A. Yep, no, that's all fine. And N is 100. So we've got 59.15. Okay, mean is going in the middle. Find the minimum sample size required in order to calculate a 90% confidence interval that has a width of no more than 2 checks per day.
It says 5 on mine.
Oh, sorry, more than 5. It says 5 on mine as well. All right. So there's a formula for n. It's 2 times 1.96 times sigma on top of w in brackets squared, I think. Let's check it. That's for proportions, samples. Yep. Okay, we want the width to be 5. And our standard deviation is 19.31. Now, $229.1. Okay, explain why I rounded it up and explain why they've allocated 4 marks here as well. So, this formula didn't used to be on the formula sheet, all right, that that SACE provides for you. So you had to calculate this based off of the confidence interval formula. So you had to get that yourself. All right, so there's sort of the 2 marks there, getting the formula yourself. And then the other 2 marks are evaluating it. But the reason we round up, okay, is because we want a sample size that's going to have a width less than or equal to 5. If we have 229, it's going to be just above 5. So we need to increase that sample size. We need to round it up in order to guarantee that width. All right, on to 12. Okay. Consider the functions e to the minus x, x squared, and e to the minus x, x to the 3. Each graph has 2 non-stationary points of inflection for positive x values. On the graph, clearly mark the location of the 2 non-stationary points of inflection. On the graph of g of x, mark the location of the 2 non-stationary points of inflection. All right, so what's going on here? I'm going to sketch the graph approximately and point it out. So this is g of x, looks like this. Point of inflection occurs when it changes from concave up to concave down. So it's somewhere here, and there it's concave down, but changes to concave up. Somewhere here. And we're not told where they're located. If you wanted to get it exact, okay, let's talk about how we would do that. I'm happy just allocating approximately where they are. If you wanted to get it exact, let's talk about how you would do it. So we'll graph the function e to the minus x, x to the 3. And we'll graph it over the same big window they've given us, which is from 0 to 10 and from 0 to 2. Alright, now I'm going to define it, that's g of x. Okay, now remember, points of inflection on the function correspond with turning points on the derivative function, alright, which correspond with roots on the derivative function. Alright, so the roots of the derivative function, we've got x is 1.268, so that's where the first one occurs, x is 1.268. And the second one, x is 4.732. Right? So you can get those points off of the graph of the second derivative, which you can use your calculator to graph for you if you want them to be exact. It's a bit ambiguous. I imagine they would accept an approximate location. Points A and B are the 2 non-stationary points. Find the coordinates of A. Okay? So here they want you to be more specific. I want you to find the coordinates of A, but on the graph of f of x. Okay, so we need to read that carefully. So f of x now is the function e to the minus x squared. All right, we want the coordinates of the point of inflection. So I'm going to graph it, e to the minus x squared. Okay, so that's the function f of x. And let's get the root is 0.586. So 0.586. And then I can g-solve that and I can get the coordinates of point A. Alright, so for you can do all of this on your calculator, 0.191. Okay, now consider the general function h of x. Looks nasty. Show that for x is larger than 0, n is larger than 2, where n is a real number. Show that h dash dash of x equals. Okay, so we've got the function h of x is e to the minus x to the n, and we need to find h dash dash. So the first thing we'll be doing is the product rule, right? U times v. U dash v dash. Oh my gosh. N x into 1. Smash all that together. So we've got h dash of x will be u dash v plus u v dash. Okay, then we need to differentiate it again, all right? So that's the first derivative. To get the second derivative, all right? Now I'm looking at this part, okay, and that's the h of x function. So I know what the derivative of this part is. The derivative of this part is going to be the whole thing we've got here. So I don't really need to worry about that part. Maybe I'll write it out here for h dash dash of x. The derivative of this component goes to negative, because there's a negative out the front, and I'll just write out the whole thing. Okay, so for the second derivative, all we've got there so far is the derivative of this first part. Then we need to differentiate this second component, for which we need to use the product rule again. And then smash all that together, u dash v. Plus u dash. Oof. And this is where you're going, gee, I hope I did all that right, because now I've got to try and factorise it. Looks right? Yeah. Okay, so we can see e to the minus x is common to all of them, right? So we can see that that's a factor that's out the front, so we can pull that one out the front first. All right, so maybe I'll do that. That's going to simplify it a little bit, and then I can talk about how we get the x to the n take 2 out the front. So let's pull the e to the x out the front, and I'll distribute this negative at the same time. All right, now looking along there, these are like terms. They're the same term, isn't it? So we can collect those. I'll just put the two out the front there and rub out that one. Okay, and we're almost there. All right, so you can see the x to the n take 2 is a factor there. One way we can think of this, right, x to the n take 1, let's just take that expression by itself. X to the n take 1 is that it's equal to x times x to the n take 2. All right, this is probably the trickiest part of this problem, if it wasn't tricky already. So x to the n take 1, one way we can write that is x times x to the n take 2. If you're using index laws, right, they have the same base, so you would add those powers, it becomes x to the n take 2 plus 1, it becomes x to the n take 1. So you can see, this is one of the ways we can write that. Alright, and so if we can write that like that, all of a sudden, this x to the n take 2 becomes a factor. So that's this term here, isn't it? So I'm going to write that out like that. 2n x to the 1 x to the n take 2 plus n take 1 x to the n take 2. And we'll do it for the first term as well. If we have x to the n, one way we could write that is x to the 2 times x to the n take 2. Alright, if you multiply if you add those powers together, that's what it will simplify to. So this first one, x to the n, x to the n take 2. Okay, then you can see where the x to the n take 2 is the common factor. X to the, sorry? X to the 2. X to the n take 2, x to the n take 2, x to the n take 2. So what do we have? X squared take 2nx plus n times n take 1. Gorgeous.
How do we tackle it ourselves? Like without your help? Like,
Yeah.
let's just say we've got something to do with making exam. Because
Well,
I've got no chance.
No, I don't think you can say that, man. Like, what have I always said to you? It's about trying to get marks, okay? So you might look at that and go, there's no way I can get there, but baby steps. Yes, you can do this, Hayden. You know how to differentiate h of x. Get h dash of x, okay? And then break it down into parts, all right? Here, you've already done that. Get yourself another mark. Here, you're just using the product rule, all right? Then you're looking at that mess, and yes, that is tricky. You might be able to fudge it. You might just be able to go equals, you know. But what am I doing there? I'm really drawing it out to show you the mathematical operations that are taking place.
So you need to close the final bracket.
That's worth 4.
Yeah, so there's a couple of easier marks, but then those aren't last two very hard. Okay. Hence show that the graph of h of x always has two distinct points of inflection. Okay, points of inflection occur when the second derivative is equal to 0 and the sign diagram changes sign, right? So this is the function we have for the second derivative. So we want to know what are the solutions when this second derivative equals 0. And I'm looking at that and I'm going, this here is a quadratic. Quadratics have two solutions. So we're finding the two solutions of this quadratic. This is an exponential, all right? So this is going to have no solutions, all right? So that means we're solving this component of it. So let's bring that up, make some space. or we're trying to prove that the second derivative has two distinct points of inflection. So let's write it up. E to the minus x, x to the n, take 2. X to the x. Okay. Now, here, let's be careful as well. Here, hence show that the graph always has two distinct points of inflection. You're not asked to find the coordinates of the points of inflection. You're just asked to show that it has two solutions. So let's think. We have a quadratic here, right? Ax squared plus bx plus c. How do we show that a quadratic has two solutions? Alright? How do we show that it has... Think about quadratic formula and think about if you want to find out if the quadratic has... Sometimes the quadratic has one solution where it touches the x-axis. Sometimes it has no solutions where it's completely above or completely below. Sometimes it has two. We want to show that this quadratic has two solutions. Does anyone remember? Find the x-intercepts. Well, yeah, we could try and find them. Yeah, and we could try and find, like, we could try and solve this. Okay. And you're absolutely correct. All I'm doing is trying, maybe I'm making it more complex by trying to talk about a simpler approach. But you're absolutely correct. If we find the solutions, you've demonstrated there's two solutions. Okay, so that would be 4 marks. All right, so you're absolutely fine. The point I'm trying to make is this one. Yeah, so remember, if the discriminant is positive, two solutions. If the discriminant is 0, 1. If the discriminant is less than 0, none. Okay, the discriminant is that inside part. So that's all you're required to show. This would be the fastest way to do it, all right? But nonetheless, you can find the solutions. That's an appropriate way of doing it. So anyway, if we go ahead for the discriminant, we've got A corresponds with 1, B is minus 2n, and C is n times n take 1. Alright, so if we're finding the discriminant is b squared take 4ac, it's the inside of that square root. So it's going to be minus 2n squared, b squared take 4 times 1 times n take 1. So this is the discriminant, and we've got 4n take away 4 times n squared take n. 4n squared.
Should that first one be 4n squared?
Yeah, good.
That was always.
But then we've still got a negative.
Negative. Because the negative 4
negative 4.
There's a negative at the front of the bracket.
Hang on, b squared take 4a c.
Because the negative is out in front of the brackets, then it turns the negative 4n into a positive.
Yeah.
Equals 4n. That's what happens when you're trying to do too many things at once as well, isn't it? I should have just done it separately and then it would have all come out in the wash. Yeah, cool. Okay, so that evaluates the 4n, which is the equation of a line, which for positive n values is positive. Okay, so for n is larger than 0, for n larger than 0, therefore two distinct solutions because the discriminant is positive. Alright, so that is tricky.
All right, I'm not gonna lie, that's tricky. Most of the marks so far have been pretty good, but those last 6 marks were pretty rough. All right. Move on. Okay, in Australia, mobile phone numbers contain 10 digits, beginning with 04. An example is, here's one. Mobile phone numbers are allocated to telecommunications service providers. Allocation is made according to the table below. A survey company has developed a machine that calls at random mobile phone numbers that begin with 040. Assume that all mobile phone numbers that begin with 040 are valid and that customers have not reallocated their mobile phone numbers to another telecommunications service provider. When the machine calls one mobile phone number, what is the probability that the mobile phone number is allocated to Telstra? Alright, so there might be a temptation here to make this more complex than it needs to be, but if you think the criteria is it must have 040, okay, you can see there's 3 belonging to Optus, 3 belonging to Vodafone, and 4 belonging to Telstra. So out of 3, 6, 10 out of 10, 4 of them belong to Telstra, so 4 out of 10, 4.4. Part 2, what's the probability that's not Telstra? The machine calls batches of 5 mobile phone numbers. Let X be the number of these calls that are made to mobile phones that are allocated to Telstra. Okay, state the distribution of X. So, X is binomially distributed. We have 5 trials, and the probability of it being allocated to Telstra is 0.4. Okay, let's do some probability calculations. Within one batch of 5 mobile phone numbers, what is the probability that all 5 calls will be made to mobile phone numbers that are allocated to Telstra? So this is talking about the event where we have 5 successes out of 5 trials with a probability of success of 0.4, which is the same as 0.4 to the power of 5, okay? Probability of Telstra times probability of Telstra times probability of Telstra. So it's that to the power of 5. 0.01024. What is the probability that at least one call will be made to a mobile phone number that is allocated to Telstra? So at least 1 out of 5, at least 1. So this is BCD from 1 to 5. Alright, and the probability of it belonging to Telstra, 0.4 out of 5 trials. And I think I've written those around the wrong way. 1 to 5 out of 5 and the probability of 0.4. Okay, binomial BCD from 1 to 5 out of 5, 0.4. Alright, so 0.9224. Alright, that was part 2. Part C. How many mobile phone numbers would the machine need to call in order to have a minimum of 99.5% chance of calling at least one mobile phone number that is allocated to Telstra? So the fastest way to do this is going to be a trial and error, right? So we've seen if you just make 5 calls randomly, the probability that at least one of them is Telstra is 0.922. We want that to be 0.955, and we're changing the number of calls we make. So this is the calculation of n. And we're just going to change this value of n until the probability reaches or exceeds 0.995. And so here's a good way to communicate it. So we saw with 5, that is 0.92. So let's go to 10. We probably don't need to go that high. But, and then probability. So we're just going to change that number. From 1 to 10. Out of 10, probability 0.4. Alright, so that's actually not so bad a guess. We've got 0.9939. Alright, so maybe we go to 12. I've got 0.9978. Alright, which satisfies it, but we need that minimum number such that it exceeds. So let's check 11. 0.996. Okay? So it passes at 11. N equals 11. So if you have 11 phone calls, you have at least a 99.5% chance of one being Telstra phone. Alright, now, see how we go. Might be the last question, we'll see. Last question we'll see. Okay, at a sporting event attended by thousands of people, individuals spend time in a queue in order to enter the stadium. The probability that a randomly chosen individual spends time T in the entry queue can be modelled by the probability density function. The graph is shown below. Calculate the probability that a randomly chosen individual will spend between 0 and 10 minutes. So it's a probability density function, which means probability is going to be area under the curve, times on the x-axis. So we're doing integral from 0 to 10 of the function 0.05 e to the minus 0.05t, and that's what we calculate. On the graph above, illustrate it, so then you'll shade the region between 0 and 10. Then shade it on the graph. Alright, calculate the probability that a randomly chosen individual spends less than 60 minutes. So now we're going from 0 to 60. Okay, if 200 individuals enter the stadium, how many does the model predict spend more than 60 minutes in the entry queue? Okay, so this is the probability of spending less than 60 minutes, which means the probability of more than 60 is 0.05. Okay, less than 60, therefore the probability of more than 60. And 200 individuals multiplied by 0.05, there's 10 poor people waiting longer Okay. Describe one limitation of the model. And it's going to be that it's asymptotic to the x-axis. Which means you could spend an infinite amount of time in the queue, alright? It's a very small probability, but infinite amount of time in the x-axis. We can just emphasize the point, small probability of spending 24 hours in the queue. it is a management policy that once inside the stadium, all individuals who spend time in a queue to buy food must be served within 20 minutes. The probability that an individual spends time T in the food queue can be modelled by this probability density function. Find the exact value of B. So the probability of being served between 0 and 20 is 1. They want everyone served between 0 and 20 minutes. So we're trying to determine this value of B. They want us to find it exactly, so there's no cheat. Use your calculator here. Because you can see we just need to calculate that and go 1 divided by it. So anyway, let's go through the evaluator. E to the minus 0.05 t is 1 on top of minus 0.05. Now 1 divided by 0.05 is 200. 20. So we'll have the 0.05 times 20. So just what did we do there? Simplified that, multiplied that out, minus 1, e to the 0 is 1, so that part becomes positive 20. And then I sharped both of those over there, so it's 1 on top of it, and I just swap them. Okay, that's the value of B. Sketch the graph on the axes. Alright. F. Let's sketch it because we're going to need to refer to it, I think. So I'll just bring both up on Desmos. So we've got 0.05. Set the V window the same, so we're going between 0 and 60 on the x-axis. And between 0 and 105. Alright, so what the point to make here is that the food function is above it, right? The food function is above it. So the question says, Is the probability that an individual spends between 0 and 10 minutes in the food queue greater than or less than spending between 0 and 10 minutes in the entry queue? Give a reason for your answer. Okay. The food queue is going to be greater because the function is completely above. So we can refer to them what they're called. The function g of t is completely above the function f of t. So, less than. Is the probability in the food queue greater than or less than? The probability is greater than, sorry, answer the question. Probability in food queue less than 10 minutes is greater than entry hang on. Is between 0 and 10 minutes, yep, between 0 and 10 minutes, as g of t is greater than f of t. 4. Alright. How are we going? We had enough? I've probably had enough. My voice is cooked already. We've got one more question, but looks nasty. And remember, this is a 3-hour exam.